So let's get started. This, if you're in the wrong room, is bottom-up code sharing with Kotlin Multiplatform. So a few quick notes about me. I'm an Android developer in the Boston area. Just started at an agency called Rocket Insights. I do some Kotlin community work in the Boston area and some open source work as well. And I'm not going to talk much more about any of the rest of that, so let's move on. Let's talk about code sharing. Why would it be nice to share more of our code? So I know a lot of us, I think, at an Android conference work in mobile. We're creating an Android app, and there's probably someone next to us creating an iOS app. And what that means is there's a lot of duplicated effort. You have two teams that are kind of solving a bunch of the same problems and kind of building these twin UIs. You also get things like accidental differences, where each team might interpret some acceptance criteria slightly differently, lead to like a product owner coming back to you with a bug that says, like, why doesn't the Android app do what the iOS app does? All of these are kind of symptoms of this idea that we often think about as programmers of keeping things dry by don't repeat yourself. But mobile development has a lot of that repetition because we have these two platforms that we have to kind of build these two implementations for. But it's not always the greatest thing to share code, right? There's a number of frameworks that have been popular over the years, such as React Native, Flutter, Ionic, Cordova, Xamarin. Often you have either some performance issues because they're doing some extra abstraction or they're adding their own runtime. You might have actually in most cases you have a new language and API that you have to learn for that framework, which you as a native developer are much less used to. And often it's the case with these frameworks that they'll be either a little bit less stable or not updated as frequently. You might be a few versions behind when you're using all of them. So along comes multi-platform Kotlin to kind of find the middle ground here. So just a quick show of hands, who's done anything with multi-platform before? Cool, not a lot of people. So give you some kind of brief rundown of how it works. Essentially, the idea is that you can take a subset of the Kotlin standard library and make it available in an environment called Common. So Common code is Kotlin code that you can run on JVM Kotlin, which is what most of us are used to as Android developers, as well as other platforms such as JavaScript or Kotlin native. So there's a number of different platforms that can build to, mostly enabled by native. And in addition to that common code, you can also write platform-specific code, which can access the particular APIs of the platform that you're running on. So we're all used to the Java interop story that JVM Kotlin has, where you can easily call into any other Java API. You have a similar ability to call into JavaScript APIs or native APIs, C or C++ API, or sorry, C or Objective-C APIs in the Kotlin native world. So a few words on Kotlin native because it's a platform that a lot of people tend to be less familiar with because it's newer. What it's doing is it's a separate backend for the Kotlin compiler that builds to different LLVM targets. So this means unlike in the JVM or in JavaScript, it's not running through a virtual machine, and it's usable on desktop, various embedded systems, and mobile. And as I said before, it has interoperability with C or Objective-C APIs that are running on the native platform that you're building to. And this enables pretty interesting space called mobile multi-platform. So that's the idea of building an app that uses JVM Kotlin on Android and uses Kotlin native on iOS. I really think that mobile is the killer app for multi-platform. So a lot of the early multi-platform use cases that kind of became more stable earlier on were JVM and JavaScript interop. So that's where I have a Java-based server and a JavaScript front end, and I want to share my data models, some kind of like validation at the interface between my front end and the back end. But that's a very limited use case ultimately. You have this kind of like one regime where you can share things, but otherwise your front end and your back end are doing very different things, and so they should have very different code. In the mobile context, your Android and your iOS app are typically essentially the same use case. There might be some implementation differences kind of because the platforms have some differences, but the thing that you're trying to do is the same, and so it should be possible to share a lot of code. As well, the platforms have very similar capabilities, right? Both Android and iOS have apps that can render some UI, they can make web calls, they can store things in files or in a database. All of these things are ripe for creating shared abstractions so you can use kind of the capabilities of either one of these platforms from some common code. So what does this multi-platform code look like? And as I dive in, a quick little note on colors. I try to kind of color code the samples in this presentation so you get a little bit of a hint of which platform they're running on. Hopefully you can also tell by context, but maybe this will help. A lot of stuff, as a spoiler, is going to be in common here, so you'll see a lot of orange. So let's look at some common code. So in common, you can do most of what you're used to being able to do in JVM Kotlin. You can define classes, you can define functions, you can do all these usual things. You have access to most of the standard library, including the collections and stream operators and stuff like that. There are certain things that you don't have. So there's not a standard library file APIs or anything like that. There's not a common threading API or anything like that because all of these things behave differently on the different platforms. But when you're doing things kind of like implementing pure logic, like your business logic, some of your architecture, that can all be defined in common. When you need to do something that's not available in common, you can do it with platform-specific code. So one way that this can look is the expect in actual keywords, which the multi-platform framework adds to the language. So this lets you say, in my common code, I want to define this expect declaration, which says, when this code runs, there will be a definition of this value, even though it doesn't exist in my common code right here. And then you can define actual implementations per platform. So in this example, we're saying, in my common code, I expect to have access to this string called platform. My common code doesn't know what it's going to be, but my Android and my iOS code both provide a definition. It will in general be different per platform because that's why you're doing this, or else you would have just defined it in common. But you're able to kind of freely make those changes. A limitation here is these definitions must be exactly one per platform, no more, no less. So it works very well as a sort of dependency injection is how I often think of it. So in my common code, I know that I want to have some value here. It might be a class, it might be an instance, it might be something. And the compiler is enforcing that I will have exactly one instance of it. Sometimes that can be limiting. And when it is, you can use something like interfaces, like we're used to, and kind of do the manual sort of dependency injection that you might have done in your pure JVM code. So we might define some foo interface in our common, have different Android and iOS implementations of it. An advantage of using this pattern is, one, you have multiple implementations. Two, your implementations don't necessarily need to be Kotlin. So maybe on my iOS app, I'm going to actually implement this interface in Swift, and I have the freedom to do that. And of course, in my test code, I might want to have a separate implementation that I can pass to do some mocking. And because these interfaces aren't one-to-one anymore, I'm doing the injection manually, nothing stops me from doing that. So that's kind of a brief overview of what the code looks like. Here's some architecture. So generally, the kind of center of your app is some common module. It might be multiple if your architecture kind of gets more complicated, but we'll do kind of a simple example. Ideally, if you're trying to share a lot of code, most of your code is in this box. And then around the edges of it, you might have some platform-specific code. So this is stuff that might vary between Android and iOS or between whichever platforms you're building to. And these then get compiled to a different format depending on which platform it's running on. So the Android code, the Android side and the common code get bundled together into a Android library file the same way as any other one that you're used to using. The iOS code and the common code get bundled together into a framework, which is iOS's standard library dependency format. And then your mobile apps call into that just like any other library. And so from the perspective of the native build tools, this doesn't look all that different than if you were just doing this natively and this was just a library that you were importing. And of course, as part of that, that means nothing stops you from also pulling in any other platform-specific dependencies that you might have that might be kind of part of your normal development flow, which means this is a very flexible sort of framework for sharing as much or as little code as makes sense without limiting your ability to do anything else that you would normally do. And of course, you also have the ability to add dependencies within your shared code. So there's some libraries available. I've written one of them. JetBrains has done a bunch. The community started to do more and more as well. And we'll talk about a few of them. So that's the kind of overview of the system. Now I'm going to talk through a project that I've been building to kind of demonstrate a lot of this stuff. So a bit of background. I like taking pictures of sunsets. And there's a beach that I go to with my family a couple times a year where we have this kind of tradition where a bunch of the neighborhood kind of gets together, watches the sun go down together. I take some pictures and I make a calendar every year out of those pictures that says kind of when the sunset is. So I had a Python script that I wrote probably 7 or 8 years ago that's doing this now. I wanted to rewrite it in Kotlin, and I wanted to kind of add a mobile app as well that could kind of use notifications to kind of alert you, oh, hey, sunset's coming up soon. You should get outside and go meet everybody. So I called that Soluna. That's Sol and Luna are the Latin names for sun and moon. So I'm being a little bit aspirational. I'm starting with the sun, but I want to get the moon too. It's available on GitHub here. And yeah, the kind of core functionality of it is to compute the rise and set times of the sun and moon, and then use that for a couple different use cases. So the ones I started out with are the calendar I just described, as well as a mobile app that can do some notifications. Down the road, I'd also maybe just kind of publish it as an API that anyone else could consume, or publish it as a library. And I should mention this is still kind of very work in progress, so I'm going to kind of walk you through some of the stuff that I've done so far. I'm still kind of actively working on it, nowhere close to finished yet. But it's a fun project. So we can talk kind of quickly through the structure of this project. It's kind of a more specific version of the diagram we just looked at. So this module in the center is core, is where the actual sunrise-sunset time computation happens. There's a pure JVM module that does the calendar rendering. So that's essentially like a desktop or a backend kind of thing. There's a shared mobile component that has the mobile app architecture that's not relevant to the calendar, but is shared between Android and iOS, and then the Android and iOS apps that consume that. So we'll kind of go through layer by layer, talk a bit about the functionality, talk a bit about some of the code and choices I've made and dependencies I've used to kind of give you guys an introduction to what some of this looks like and what I've done so far. So core, as I said, does the rise and set calculation. So there's a bunch of kind of math and trigonometry and stuff to that, but essentially we have some formula that tell us in a certain coordinate system where the sun and moon are in the sky. We kind of transform that to the local coordinate at which it's right on the horizon, a little bit of a kind of solve for x, and we get what is the actual time at which the sunset happens. As part of this, I wrote a bunch of utilities around doing math with degrees. So your typical computer language trig functions work in radians, but astronomers really like degrees for kind of historical reasons. So I wanted to be able to kind of use the formulas that I was reading about in some textbooks, kind of at face value. So I have a bunch of kind of degree radian utilities for that. Another kind of fun note about core, I've tried to include no external dependencies at this layer. I'm trying to kind of keep it flexible because I'm not sure exactly where I might want to evolve it to in the future. So that means there's no date time abstraction that exists in common Kotlin. So core is not able to leverage anything like that. And still work to do here. So I've gotten the sun calculation mostly working. I had a first draft of the moon calculation that isn't quite working, and I can't figure out why, so that's in my to-do. But the API of it is fairly simple. There's really kind of two public functions that it exposes. There's one for the sun times and one for the moon times. They take in essentially the date, an offset to kind of hint at the time zone and the position, and they output a pair that's the rise and sun times if they exist. Sometimes, if you're at the right latitude, there's a date where they don't, and returns that. And as I mentioned also, this includes those degree and radian utilities. So I have this kind of angle unit abstraction that it uses internally. That can be a degree, it can be a radian, it can also be this unit called an hour angle that astronomers use in some contexts. And then it defines kind of aliases of the trig functions to be able to do math with these. And I've been making use of inline classes to make the typing of that easier, which has been an interesting experiment. So one of the consumers of core is that calendar layer. It's pretty simple right now. There's kind of more I want to build out, but it's mostly doing ADUT drawing commands, and it's using Java.time APIs for date manipulation, and it just renders an image of a calendar screen. A lot of things still to do here. There's not much in the way of architecture or tests on this layer yet. It hasn't been my focus, but I wanted to kind of get the first pass of it working. I want to give it kind of a good command line interface to be able to make it, like right now you just have to edit source to pick which value you're going to use, which isn't that clean. So that's still on my to-do. And it'd be neat to kind of, I've been wanting to dig into Tornado FX, which is a JVM like desktop UI framework. So I was thinking this could be a neat test case for that, but I haven't done any of that yet. But the core of the logic is it kind of iterates through each day in the month. So you give it a month and a year. Iterates through each day. It computes a local date. It passes values from that into that core API. So that's that sometimes call. And then it converts the output of there back to a date time, which it can then use to render. And in the end, with another kind of 100 lines of code that I didn't show you, you get something like this, where you have the full kind of calendar grid with each date displayed with the sunrise and sunset times for each. So that's all well and good, but this is an Android conference. We're here to talk about mobile, so let's talk about mobile. So the mobile app here, the main functionality is to configure alert notifications based on the rise and set times. We're going to store that configuration in a database using the SQLite library. And we also have a API layer where instead of just needing to input each coordinate manually, which is a bit of a pain, we want to be able to put a location name in and ask an API for those coordinates. So the Google Maps API has functionality for this, so we'll define an API client to do that. And then with all of that as kind of our input data, we want to schedule and generate alerts using the native APIs. So a lot of things still in progress here, but I'll walk through some of the stuff that I've done so far, starting from the kind of core data models. So we have a location, which has a name, has longitude and latitude for its position, and a time zone, so it knows which times to output. And then there's a reminder model that says, I want to set a notification for a given location that has a type, so it might be like a rise or a set, and it has sub-specification for minutes before. So like I might want it 5 minutes before, I might want it half an hour before, depending on what my preferences are. And there's like a many one-to-one relationship there, because I might want to have multiple reminders for a given location. And we can take a quick look at the kind of overall architecture of the mobile side of this. So at the bottom, there's a database that stores those models that we just talked about, and then there's API classes that give us the ability to make those web calls. There's a repository layer above that that kind of coordinates all of that together, and then view models for each screen. And I've tried to use a coroutine-based architecture throughout most of this. It's a little bit funky in spots on the native side, but for the most part, I've made it work. So we'll kind of go through each of these bit by bit, starting with the database. So the thing driving the database layer is a great library from Square, mostly written by Alex Strong of Square, called SQLite. You can find it there on GitHub. And what it does is generate, it's a little bit like an inverse Room, where Room you kind of, you write your data models and you write your database access object classes, and then you annotate it with SQL to kind of force it to all match up. SQLite, you just write your SQL and it will generate Kotlin code to do all of the rest of that. So in brief, what it looks like is you write some SQL like this to define, this is our location table that has those fields that we talked about in that data model. We can define different functions we can use to access that database. So there'll be a select all locations function that gets a summary of some of that data from that table and returns that. And that SQL generates functions that look essentially like this. I've kind of trimmed down some of the details. But we get a data class that has all those fields, and we get functions we can call to do those queries. So some more details on SQLite. So most of the configuration you do for it is in common, but you have to pass it in a driver which is platform specific. So there's like an Android SQLite driver and a native SQLite driver. You can use SQLite on other platforms, but there aren't kind of built-in drivers for them. So if you wanted to like do something in JavaScript, for example, you'd have to supply your own implementation. A neat thing about both of these two drivers is they have the ability to do in-memory versions instead of just disk-based versions, and that's very helpful for doing your unit testing. Initially, most of the code that it generates defines kind of separate interfaces and implementations, which is another thing that's really helpful in the multi-platform space when you're trying to do some testing. So that's the database. Moving on to the API client. So the backbone of making a mobile API client in multi-platform Kotlin is Ktor. So you might be familiar with Ktor as JetBrains' kind of pure Kotlin web server, but it also includes a HTTP client, which is multi-platform, which is available on all platforms. And within it, it integrates very closely with coroutines, so that the kind of APIs are all coroutine enabled. And it's very easy to work with Kotlin X serialization, which is JetBrains' cross-platform serialization library. So essentially doing the work that you might use JSON or Moshi for on Android. So don't worry too much about all the little details in here, but what you end up doing is you can define a HTTP client. You pass it in an engine, which will vary per platform. You can define some default request parameters that, like your base URL and some API keys that will exist on all platforms. And you can configure various features, which include, like JSON feature is what does the automatic JSON serialization. So here you can see it configuring configuring the Kotlin X serializer to be aware of the different web response types that we use. And once you have that HTTP client, then you can define the actual kind of functions that you want to expose. So I can make a specific web call by calling get on that client, passing it some URL parameters, and we get a suspend function that returns the response type that we want. Similar to SQLite, you do a lot of the configuration in common, but you also pass in separate per platform engines, which lets you kind of do your platform specific behavior. A neat thing about this one in particular is like by default, it's easy to do, like there's a HTTP URL connection one that you might use on Android, but you could also, if you have an existing app that's using something like OKHTTP, there's a KTOR engine that interoperates with that as well. So if you're kind of mixing shared code and a kind of pure Android app, you can share your OKHTTP configuration between them. There's also a mock engine that you can use for testing. So in your unit test, you obviously don't want to be making real web calls. You can configure this mock engine to make your test work that way instead. So on top of those kind of data sources, essentially, is my repository layer. So that's kind of the central data layer that kind of pulls all these APIs together. So it wraps the SQL calls in suspend functions, and it kind of coordinates that geocode process actually takes 3 different web calls. So it kind of coordinates that together so that the view layer only needs to know about one call. So before I jump into kind of what that looks like, let's talk about the threading model of Kotlin native. So native threading is hard. So the Kotlin team has chosen to be, at least at the current point, this might change in the future, but they've chosen to be very opinionated about not allowing mutable state to be shared between threads in Kotlin native. And that can mean that a lot of patterns that you might be used to in the multi-threaded JVM world don't work as well as you're expecting. The way they enforce all of this is that they have this concept of freezing an object, which is kind of a hardcore version of immutable. And an object must be frozen to be able to be passed between threads. And what frozen means is that object can never change, and anything that it references also gets iteratively frozen. So if you're not careful, you can kind of accidentally freeze all of your state that happens to be getting referenced from something that you froze, and then the next time you try to touch it, you get an exception that says this is frozen, you can't change it. So all of this is runtime enforced, because at compile time you don't know exactly what's been frozen. So it can make kind of doing multi-threaded things in Kotlin native a little difficult. And in particular, like there's kind of different mental models that you have to use for doing native stuff and JVM stuff, and so it's not easy to kind of wrap that into a kind of common API. So I've done this thing that sort of works. It's a little bit fragile in that when I've kind of made small adjustments, sometimes it starts crashing on me. But I have this run in background function that on the Android side is implemented using coroutines. And then on the iOS side, it's implemented using the Kotlin native worker API, which is how native exposes different threads. So the kind of thing to watch out for here is on the native side, we're taking in a Lambda block. We are, there's kind of 2 lambdas on the bottom here. The first one is the input, which says we're going to take that block, we're going to freeze it, which we need to do before we pass it between threads. Then the second lambda is the part that actually runs in the background. So we have that lambda, we invoke it, and then we call future.consume, which blocks that thread until it kind of finishes and has a result. And then we resume our continuation to kind of pick up our suspend function. So what's dangerous here is if there's anything kind of referenced from that block that you weren't intending, then it's going to get accidentally frozen. And this, as I've been developing this piece has felt very unstable. Like I've kind of made small changes and suddenly it starts crashing. So still kind of working on cleaning that up, but just kind of things to watch out for. This has mostly worked for me so far. And then once we have that ability to run in background, we can kind of wrap our SQL queries in that. So we have a get locations call. We pass it to that running background. Inside of that lambda, we do our, this is the generated SQL Lite API, which then returns a list of location summary objects which were in the database. And then in addition, we have the API layer where we make a couple different API calls. So each one of these calls is a spend function to that KTOR client that we talked about earlier. And then in the end, we combine it all together in a net object. So on top of the repository, we have a view model layer. So I'm still kind of very in progress on this. There's kind of one that I've been mostly focused on, but I'll talk about kind of the general architecture. The view models take the state in the repository layer, expose it to the different views, and they're the platform interop boundary. So there's a couple things that you need to be kind of careful about to make sure that both platforms can kind of work with this, because the Swift UI layer, sorry, the iOS UI layer is written in Swift. So I use a callback API where each platform can kind of pass a callback into the view model to say what it should do when its state updates. And we can't have public suspend functions at this level because Swift isn't able to call into them. But the kind of general structure of view model, in the center, it has this state value, which is kind of generified by the type of the view state. And we use delegates.observable to call out a listener every time it changes. And then I have this internally with this kind of update async utility, which is sort of doing like a reducer sort of functionality where it launches a coroutine that updates the state. And then when that state changes, it will call that listener. And then for the kind of like real calls that the view makes, they just kind of wrap that update async and pass a lambda in that does that work and then returns the updated state. So we take our state, we copy it with whatever change we want to make, and we return that from the lambda. So dirty secret, I'm here at an Android conference, but the only mobile side work that I've done here is just the iOS app, so sorry about that. We'll talk a little bit about the kind of one iOS screen that I've written so far. It's the screen where we're kind of adding a new location. So we have fields to type it all in manually, or we have a button that can call that geocode API to populate it automatically. So yeah, all written in Swift and Xcode, calling into all this Kotlin stuff that we just talked about. And it consumes the view models and renders UI out of them. I think that's helpful here that not many people know about is JetBrains publishes a Gradle plugin called Xcode Compat, which can, it's part of the app code samples if you try to do your development in app code. And it has tasks to export your Kotlin framework to an Xcode project and even to generate that Xcode project for the first time, which can be really helpful for setup. So it's available at that URL if you're interested in it. And then, yeah, essentially the iOS app, sorry? Oop. Yeah, you want the URL. Sure. So yeah, inside the iOS app, we define view controls for each of these screens. They reference, there's kind of a top-level repository that's defined in Kotlin, which the view controllers can then pass through their view models, and then they can define this thing on the bottom is a click listener that does that geocoding action. So a couple other just kind of little tips and tricks coming out of the iOS layer. One thing that Xcode Compat plugin does not do, though I opened an issue to hopefully they'll add it, is to run your unit tests on iOS. So by default, Kotlin native will generate testing tasks for the platform that you're developing on, which in my case is often macOS. But you need to kind of set up this manual Gradle test to actually run these tests on the iOS simulator. So you can find this code sample at a bunch of different places because pretty much any Kotlin native example or iOS example will do something similar. This is what it looks like in the Kotlin Gradle DSL. A couple other fun notes. One other dependency that I use in here that I haven't talked about yet is called build config with a K. And it gives you essentially a multi-platform version of Android's build config tool. So this is really useful if you want to be able to inject some field from your Gradle script. So I use this for the Google API key that we need for the Google API client. Another useful trick is so traditionally, Kotlin Native does not expose any generic information to Objective-C or Swift, but there's an experimental flag you can pass to the compiler to turn that on now. It doesn't work in every situation because the generics models of Swift and Objective-C are different from each other and different from that of Kotlin. So there's kind of some use cases that work and some that don't, but it's helpful to be able to get something. A couple other helpful notes. So there's a couple debugging tools that exist on the native side, relatively new. I haven't played with them all that much, but they're there. So app code has one built in from JetBrains, and the paid version of IntelliJ IDEA has one as of the most recent early access version. I haven't tried that out yet, but it's there apparently. So it seems, as I understand it, the model that JetBrains is going for with native stuff is you can do your development from the free versions of things, but things like debugging are part of the paid product because they have to make money somehow. So be aware of that as you're kind of doing more and more complex things. In addition to those two, TouchLab and Kevin Galligan, who I don't think is in this room today, have made a plugin for Xcode, so you can, instead of doing your debugging from the JetBrains IDE, you could do it from Xcode, which is a little more natural to your iOS team. One unfortunate thing about that is part of that is a Gradle plugin, which isn't compatible with that other Xcode compat Gradle plugin, which I mentioned earlier. I think that'll change at some point in the future. There's an issue open for that as well. And then I guess a reminder, you might have noticed a kind of theme with all of these dependencies that I walked through, that a lot of them kind of define their own mock versions, interfaces, and things. There's not a cross-platform mocking solution right now, which means if you want to be able to kind of like create fake dependencies, you end up doing a lot of manual work. So be aware of that as you're kind of doing more and more complex multi-platform things. So I have a bunch of to-dos still on here. I'm very much still in progress. I've talked about I've done a kind of full vertical slice of the location data type and that one kind of add location screen. I need to do the same with the reminder types to port that up through the repository layer. There's a lot more UI to build. So yeah, a couple different screens in iOS. There's the whole Android client that I haven't gotten to yet, somewhat embarrassingly, as I'm presenting at an Android conference, but I'm getting there. And then, of course, most of my mobile side work so far has been focused on the configuration side. Once that's there, I need to build the notification API that will read into that and actually generate the client-side notifications. And ironically, like that's the piece that's actually going to call into core. So nothing I've written on mobile yet is integrated into the bottom layer, but I'm working on it. So what are some lessons I've learned along the ways? So there's a bunch of great libraries. Here's them kind of listed again that I talked through a little bit earlier. So there's SQLite for databases, there's coroutines for async stuff, there's Ktor for making web calls, serialization for serializing your JSON responses, and build config for injecting data from your Gradle file. And we have a nice ability, as in principle we do on any platform, to create this layered architecture to separate our different concerns so that we can share the kind of inner layers that make sense to be shared and you want to run on every platform, while still being able to define separate implementations for the things that want to behave differently. So we share what's worth sharing, and we are free to not share what's not. And that's what I think the great thing about multi-platform Kotlin is. So thanks. I think we're probably a little tight on time for questions, but you can feel free to come talk to me after, or tweet me or Slack me. I'm on the Kotlin Laying Slack. I'll leave this links page up for a little bit too. So the project link is at the top there if you want to go through my code. That second link is a great set of documentation of the kind of pretty up-to-date documentation on how to do the different multi-platform Gradle configuration, which I didn't go into too much detail on, but it's there. And then a couple resources on where to find different multi-platform libraries. So there's not a ton of it up there yet, but there's more and more that people are starting to write. So come check out this space. It's pretty fun. And yeah, that's what I've got. Thank you very much.